Your computer?
Like the sorting out process, right? It should be more intelligent than that. It's going to be something like that. We're going to keep trying. You're going to know if you get okay, right? But
so on your computer, you're going to want to log into
and you can say yes, probably. You can actually bound the expected
into this.
Right, like for the coupon collectors problem, right? I bounded the expected. Yeah, so I looking at the linearity of expectation each time I get a distinct response. I know how many trials you expect it to take.
We have students that come in that aren't here, like they're actually in different programs that are like not local. So it's for them. Yeah.
So I should.
Yep.
Total expected.
You can also watch these videos afterwards if you like.
Yeah, I've been watching last week for like live. I'm about an hour and a half away. My day isn't new.
Yeah.
I was just curious why you did it for such few people. If there are students elsewhere, I didn't know about that.
Yeah, there aren't a lot, but yeah. You want?
Okay, so you're doing tweaks. So you're looking at so explain a little bit more. So let's say viable. Which is weird.
Are you on Wi-Fi? Yeah. So now you want to log into that.
Yeah, so it's trying to predict the sentiment from the. So I wonder. Yeah. Okay. So I think it's interesting. So there are some things we'll talk about.
Yeah.
We'll start going towards that. We're not going to get into. The best way to do that is using that process to actually understand the we're not going to get into that. Right, but there'll be some techniques we can use, and they're going to be things that are going to be more very scalable. So you can use that.
UU.
Oh, you.
So
Dot.
I think it's an interesting.
No, the dot doesn't matter.
But, as long as you're picking out some ideas from class.
Try.
This
And I
one.
think there are plenty of things you can use.
No, it's fine.
You of your data.
Yeah. Did you put the UU?
Oh. Okay, and
If you go up to the YouTube.com, you want to go to the live stream. You just go up to the URL and write live stream after YouTube.com and it'll pop up. /live stream. Yeah, try that. Or no, sorry, underscore live stream, live underscore stream.
There's some questions. I think some of the interesting questions are what people get out of the class. How to take data like that and turn it into a format where it makes sense to run a cluster.
Oh wait, that didn't work. If you navigate around, it should be there somewhere.
Okay, so you think that class, what they'll do is they'll break down the try and analyze this word is and those techniques can be really powerful. But they're more low level than
Sorry, I actually don't remember where this is. Oh, video manager, that's where.
We're going to do is try to say what I think what we're calling part of trying to guide you so it fits within the scope of this class. We're trying, it's part of the data analysis process. It's like, to make sure you're not really giving up
So, and then
You're good. If anyone like posts a question in here, just say something like
so now the stream is recorded. So when the class is over, I just click.
yeah, just click that button, then wait till that stops. There's about a 15-second delay.
15 seconds.
Yeah.
I mean, when the class is over, I should click this one.
Yeah, and then wait like about 15 seconds until that goes blank.
I should click this one, record.
No.
This one.
Yeah.
Stream.
That'll kill the stream.
Kill the stream. So and then wait 15 seconds.
Yeah. Until that goes blank. That'll go blank at some point.
And then I can close out.
Yep.
Thank you.
Oh yeah, no problem.
Thank you very much.
Yeah, no problem. If you have any questions, just send me, or do you have my phone number?
Let's get started. Hey, I know it's a long weekend. You all had a great time. Maybe skiing. How many people went skiing? How many people, or snowboarding?
Your phone number.
Or how many people stayed far from the snow as they could? All right. Okay, good. So the long weekend's over. We're back. You may have even done something on Tuesday. So we're back in class. So a couple of notes before we get started. So we changed. So Michael changed the room number on where his office hours will be. He got an office in I think it's the big TA. It's the bullpen. There's a room there. So look on the web page. I've changed his office number. That way it's not up the stairs, but the same general area. If you haven't seen, homework 1 is posted. A bunch of you have asked questions about that already. That's great. Hopefully that's going okay. It's not due for a few weeks still. Remember, it's due on January 27th. So that's actually in a week. Okay, so it's due in a week. So you can make sure you get started on that. Hopefully it shouldn't take too long. I've asked you to scale. I've asked you to run these small experiments and to plot stuff, and then to scale a few of them up. And where I scaled them up to is about where it's going to start to take a long time to do it, but it should be a reasonable amount of time to run. If it takes over a day to run one of those things, you may not have implemented the most efficient way. Okay, but I don't care too much about if it takes a long time to run. I kind of want to make sure that you can do it. If it takes a long time, you're going to have to wait. I'm not going to have to wait. So, question.
So 5 hours isn't unreasonable?
It's fine. So if it's done, if it works for you, if you did it and it took 5 hours, I'm not going to say do it over again faster because you've already done it, right? So often this is the case, right? When you're doing data analysis, you have to trade off how long does it take me to write something really fast versus let's just run it and then I don't need to use this again. If you think you're going to use this again, you may want to really make it optimize it. You're always going to have those trade-offs. And I understand if you say, look, I just run it once, it takes 5 hours, it takes 20 hours, but once I'm done with it, that's fine. So I'm flexible in that way in this class. I'm a pragmatist in terms of these things. Okay, and then the week following that, on Monday, the proposal is due. A few groups have started talking to me about projects. That's great. Start finding groups. The projects will need, you will need at least one partner unless very special circumstances, okay? So groups of 2 or 3. And if you turn in a proposal where you do not have partners, then you will lose points unless it's been approved by me. And it's not always I approve it. If you turn in something, if you can't find a partner, you turn in something without partners, I will pair you up that way. It's easier if you do it yourself. People have posted already on the discussion group. That's great. So go ahead and do stuff like that. And just kind of find topics that you're interested in for the project. The main thing is it should be something that's related to the scope of the class, and feel free to ask me about that. I know data analysis in general goes across many classes we teach here, and I'm kind of flexible, but I don't want it to be a project that fits dead in the middle of another class. It's better you learn what we teach in this class instead. Right? So that's the main reason for that. Okay, so then we'll get into the lecture today, and we'll start actually thinking about how to look at actual data. And so we're going to talk about Jaccard Similarity and K-grams today. And the basic idea is that we want to understand which documents are similar. Okay? So we're going to have a set of documents, and just think of it as a file with text in it. And we want to know which ones are similar and which ones are not, right? So what are some examples of this? So the first one, maybe relevant for the class, is homework assignments. You pass a homework assignment, I view it as a string of text. If 2 are too similar, well, then you might be cheating. And so the algorithms we'll start talking about today and kind of continuing over the next few classes are kind of the basis, the very low level basis for how there's software out there that professors have access to, where we can run, and if 2 assignments or 2 pieces of code are too similar, we can tell. And so what does that mean similar? We'll get into this, but we'll give you the basics of where these algorithms come from. So don't cheat in this class. I'll be able to figure it out, right? So another application of this are for web pages, right? So this is really important for search engines like Google, because when you search for a keyword, they'll show you like a list of top 10, right? So what they want is that the top 10 pages are distinct. So that if you get pages, they don't want all the links to essentially be the same web page. Just, there are a lot of web pages out there, and this is better now than it used to be, where it's just a copy of another web page that someone's taken and put a bunch of ads on, right? And so you don't want to get a bunch of these. You want to find distinct, different things you can click on in a search, right? So if they're distinct, they should be far apart in some terms of some distance, right? They should not be similar to each other, right? So this is an important problem for inside search engines, and this didn't used to be optimized. It used to be when you would search, 5 of the top 10 choices would be essentially the same content. And this is not as much a problem anymore. They figured out how to do this, and this is often based on the way of thinking of similarity between these documents that we're going to talk about. And then the other one, another very important application of this is if you're dealing with email. Similar between email is kind of really important for detecting spam. Most spam detection, the easiest, one of the most effective ways to do it is what's called is based on this basic technique called threading, where they'll take a known spam email, and if there's another one that looks close enough to it, it's probably spam, right? So most spam emails are basically the same text sent to lots of people, right? And so if they see lots of these emails that are exactly the same being sent out, that's probably spam. And maybe it's not spam and they can mark it and say, okay, it's very similar to this one, but this one's known not to be spam. This is a warning message that, you know, your account has been broken into or something like that, right? That is not, so that you can flag them either way. But you need a notion of which emails are similar to each other, okay? And so the basic way of doing this, and the thing we'll think about, is that you're going to have some document, and this is going to be full of words, you know, and it's going to have more words. And so we're going to take this, and we're going to think of mapping it to into something. We're going to map it into something called a metric space. And so typically when you think of a metric space, the most common example, which is not what we're going to use, but just for illustration, is you map it, so you can think of it as a point in this space. Okay, and the most common way of doing this is that you can think of this as this point in a point in a Euclidean space. Okay, and so then you'd have another document. This also has words in it, and so this one maps to a different point over here. And so now you can look at the distance between these 2 points. And we'll call this point P and point Q. And so if this distance is small, they're similar. If it's far, then these documents are not similar. Okay, so the challenge is to take these documents and put them in some space where the natural distance in that space tells you something useful about the documents. Okay, and so we'll talk about a few ways to do this with documents over the next few classes. It's a great example. It's just one example of this problem, though, where you have some abstract type of data, and you need to map it to some place where you can measure the distance between them. Okay, so if you do it in this Euclidean space, what you've essentially done is I've said that if it's in this d-dimensional space, then I'll say that P, this point here, is in RD, and so what this basically means is that this point has coordinates P1, P2, up to PD, and then the distance between P and Q would be measured as, so this is the standard Euclidean way of doing it, is it's going to be the sum over I equals 1 to D of Pi minus Qi squared. And we'll come back and talk about these sorts of distances later. This is kind of the standard thing that's very easy to work with. And I'm putting this up now just so you're getting used to some of this notation if you haven't seen it before. The main thing, if it say it has coordinates, and I put these round brackets here, this means if I change P1 and P2, it's going to be different, right? So this is not equal to P2, P1, PD, right? So if I switched the ordering of these, that's a different point, okay? So the reason I mention that is because what we're going to do with these documents is we're going to map them into a different metric space where the objects we're going to work with are going to be sets instead of these essentially high-dimensional vectors. Okay, and we'll talk about these vectors much more later in class. But we're going to talk about sets, and it's going to have a different notation, where instead we're going to say it's going to be a curly bracket, and these indicate that it's going to be sets, and then the ordering of the things inside does not matter. Okay, so let's go and do this now. So hopefully you've seen I've fixed the pen. Hopefully the drawing looks a little bit better now. If any of the colors I've used is not showing up at all or something, please let me know. Anything like that. But yep.
A couple questions. So can we think of P1, P2, the different discrete things in the set as words in the string?
So that's gonna be one way of thinking about it. Yeah. So we'll that's kind of the basis, and we'll get to that. I'm going to build up to that a little bit.
And then just kind of conceptually, I think from the text I kind of understand measuring the difference in distance and difference in similarity, but I'm having a hard time wrapping my head around taking a string of words and mapping it to a point.
Yeah. So we'll get to this later. In fact, the string to a point we'll not get to in this lecture. I think the next lecture we'll talk about to a point. We're going to map this document into a set instead. Okay, but first let me just talk about sets and the distances and similarities we use on the sets, and then I'll come back and say how do we take the document and turn it into a set in a way that makes sense. Okay, there are lots of little issues that come in here, so let me kind of build this up gradually. Okay, so the important thing, we're going to work now with these sets, and so a set A, B, C, this is going to be equal to A, C, B. So I can change the order here. And so there's some subtle differences you'll see, like if you have a multi-set or not. So that means that, so maybe this is equal to A, B, C. And so we'll talk about things where these two are also equal, where I just care about which elements are in there, not how many times they occur. Right? So A's occur twice, but it's still the same, because it's the same set of elements. And I probably shouldn't even, in some cases you shouldn't even write it like this. But in general, if you put A into a set that already has A, it does not change. Okay, so now, as you were alluding to, we're going to talk about not just distances, but also similarities. And with sets, it'll be more natural to talk about the similarity between sets. So it's probably, you're probably more familiar with the terminology. You say the distance between something. Similarity is just kind of the opposite. If you look at, I'll say something like the distance between sets A and B, and the similarity between sets A and B. And so, the distance is basically small if A and B are close to each other, where the distance is small if they're close, where the similarity is large if A and B are close. So you see they're more similar, it's larger, right? So this is just a kind of they have a function from these two sets or two objects, and that's going to freak me out all semester, isn't it? Okay, so it's a function from taking in two sets and mapping to a number. So often this distance will map to a number between 0 and infinity. This is typically the case. Sometimes it maps to a subset of this, like 0 and 1. Sometimes the distance can be at most 1. Whereas similarity will often be in the range, will map to 0 and 1. This is much more common. So the things are most similar, the value is 1. They're least similar, the value is 0. So if the objects are the same, if A equals B, then usually this means that the distance goes to 0. If A equals B in the similarity, then the similarity usually goes to 1. Okay, now this isn't true for all distances or similarities, but this is kind of the general idea, right? So we'll talk about, and you can often convert between these. There are a couple ways of doing that. For the similarities we'll talk about today, the most common way to do it is the distance is equal to 1 minus this similarity, this. Okay, so we'll define the similarities, and then you can define a distance by doing 1 minus the similarity is the distance. That's not always the way you do it. There are other cases where it's more complicated, where the distance looks like SAA. minus 2 SAB. Okay, so this should look like kind of if the similarity defines an inner product, if you know what this means, then this is the natural distance. So if this is the dot product, then that's how you get a Euclidean distance out of it. Yeah.
Earlier you mentioned items in parentheses, order is dependent or is important.
Yeah.
In this case, the distance from A to B or B to A is equivalent, right?
So in some cases that's going to be true, not always. So later in a few more lectures we'll talk about if a distance satisfies satisfied property that says the distance is a metric. In that case, you need to have this symmetry and other properties. But you don't always want to use metrics for various regions, and we'll talk more about this. That's a good property to have often, but not always.
SAA and SBD, if S is going to be 1 if A equals B, wouldn't those just be 1?
Yeah, right. So in the case where A equals B, you get a value of 1, then this would be 1. But that won't always be the case. These are kind of general rules, but not always true. So we'll see some variations on these throughout the class. In the class we'll talk about today, we will focus on this conversion, which will make more sense, and this will be true as well. But we'll see some, like if you think of just like a dot product between two vectors as a similarity, then that does not hold, and you want to use this instead, for instance. So some of these are general rules. I'm just trying to give you an idea of the space of these things right now and some ways to think about it. Okay. Okay, so the main, when dealing with documents and the sets that will generate from them, the most common similarity is called the Jaccard Similarity. Okay, and so I'll kind of have a running example here. 1, 2, 3. B equals 2, 3, 4, 6. Okay. So the Jaccard similarity, and I'll write this like this, between A and B is equal to A intersection B, A union, divided by A union. So the size of the intersection divided by the size of the union. Okay, so I can write this in notation like in this Venn diagrams. And these. Okay, so it looks kind of like they're supposed to be the same top and bottom. Let me fix this. Okay, so now the divide these over each other, the intersection divided by the union of these sets, okay? So hopefully this is clear, right? So this is the Jaccard distance between sets, right? So in this example, this is going to be equal to, the intersection is going to be equal to 2 and 3 over the size of the union, which is 1, 2, 3, 4, 6. So this is 2 over 5. So if I write these vertical bars around a set, that's the cardinality of the set. That says how many elements are in it. Okay, so that's the size of the set. So there are 2 elements in the intersection over 5 in the union. So 2/5 is the similarity. Okay, so if two sets are the same, what's the Jaccard similarity going to be? Well, it has to be 1, right? Because the intersection is equal to the union, right? So, and the more different they get, by either one set gets bigger, or they both add elements, or you take stuff out of the union, the similarity is going to go down. It works kind of naturally like you'd expect. The more different they are, the smaller the similarity. And so the sets don't have to be the same size. And you know, I don't need. And another nice property we'll see is, we'll illustrate it more in another class, is that I don't need to know some total superset that all the elements come from, right? Could 10 have been in either of these sets? I don't know, I don't care. I didn't see it in either of the sets. This, in other definitions, this will actually come up. This is the Jaccard similarity that we'll talk about. Yeah.
You said that similarities usually fall between 0 and 1. Are there cases where it doesn't fall between 0 and 1?
Yeah, so not, I mean, in all the ones we'll talk about today, it'll fall between 0 and 1. But there are other notions, like if you have vectors instead of sets, then you can think of the similarity as being the dot product between two vectors. If the vectors are both large, it doesn't need to be between 0 and 1. But in this case, it will be. Yeah. Yeah.
Well, what if both the sets are empty? Then will they be the different?
Yeah, so if they're empty, you could, let's see, choose to define as either 0 or 1. But basically, you won't run this if they're empty. Let's, I can make an arbitrary decision and say empty if either of the sets is empty, or if both the sets are empty, then the similarity is 0. Let's say the similarity is 1 because they're exactly the same. Okay, there you go. That makes good. But these are kind of minor points. You would never, if you knew it was empty, you would never run this, for instance. But you can define it however you want. Yeah.
But if the cases are mutually exclusive, like the union didn't contain any elements, so you have a division by 0.
If the union of them is kind of, if neither of them are empty, the union can't be empty. The intersection might be empty, right? So if they have no elements in common, the similarity has to be 0, right? So the distance has to be 1. Good. It's always, when you see these things, it's always good to think through these boundary cases. It really helps you understand what's really going on here. Okay, so one more thing before we talk about using this with actual documents, I just want to give you a taste that, you know, we're going to talk about the Jaccard similarity, but it's not the only similarity here. So let me just go through a few of these. Like there's this nice class of similarities, and some of you may choose to use them for projects. They might come up in the homework. We'll have to see. But before I define this nice class, let me just define one more operation. So you might not be familiar with the symmetric difference between set is defined as usually written A triangle B. And so this is equal to A union B set minus, run out of space here. A union B set minus A intersection B. So the set minus operation, which is this guy here, it takes out the elements in the intersection, right? So if I drew my picture here again with my Venn diagram here, the symmetric difference is going to be this part here in A that is non-B, and the part that's in B but non-A. Okay, so this symmetric difference kind of, and then The one other thing we may need is the complement of a set. So A bar is equal to, let's say, everything in the space I'm in, set minus what's in A. So this would be the whole universe that the set could be pulled out of. So then you would think of, that would be the case where you have some space, which is the whole universe, and I'll just write like a set of n things, for instance, and then I have my set A, and then the complement is everything that's outside of here. Okay. Okay, so for the complement, I need to know what is this full set. I didn't need to know this in the case of the Jaccard distance. Okay, so there's this general class of these similarities that's been studied, and I'll just write this in this abstract setting, and then I'll give you a few examples that fit into here. And I'll probably leave it as an exercise of what the values x, y, and z are. But you can write them as x times A intersection B plus y A union B complement plus z A symmetric difference B over A intersection B plus y times A union B complement plus z prime A intersection A times the size of the symmetric difference of B. So a lot of if you're looking at similarity, if it fits in this form for values for some choice of x, y, and z prime, it's probably a similarity that kind of makes sense. So most ones you can fit into this framework using these operations. So for instance, the Jaccard similarity between A and B is going to be equal to S1, 0, 0, 1 of A, B, right? So what I've done here is you can write this as A intersection B over A intersection B plus A times the symmetric difference of B. Okay, so the intersection plus the symmetric difference is equal to the union. So by doing this, I can recover the Jaccard similarity. But there are a few other ones I'll mention. The Hamming similarity, that's going to be equal to 1 minus A times the symmetric difference of B over the size of the whole set. This is the size of this. Okay. So what would if I wrote this as this general function S of x, y, z, and z prime of A and B, what are the values going to be for the x, y, z, and z prime? So a useful way to do this, I don't see anyone doing this yet, is to draw the Venn diagram, the two parts that this would do. All right, so let's go and do this. Okay, so let's start with just the Venn diagram of this part here, and then we'll do 1 minus, which will be the complement of it, right? It's everything else. Okay, so if I have my A and B, and so we'll draw this on the top. It's going to be the size of the symmetric difference, which is going to be this part here and here. And then on the bottom, right, so I'm going to get, it's going to be the size of everything. Okay? So now, how would I deal with the 1 minus this, right? So basically, I can make this the size of n. I can put the size of the whole set over the size of the whole set, right? That stays in the bottom. So now I just need to flip the top, right? So then essentially I'm taking the complement of the top here. And so it's everything that's outside of here plus the stuff in the middle. Okay, so this is what the Hamming similarity looks like. How would I choose x, y, and z's so that makes it work? I somehow need the bottom part. Up. I can't quite point to it. Up. Make it a shadow. No. Okay. So up here in this fraction to equal 1, right? I need so I need the denominator to equal 1. And so I need and then I want the top to equal the union, or the intersection plus everything outside, right? And so keep in mind the middle term is the complement of the union. So that seems like a good thing to have in there, right? If I set y equals to 1, I get the complement of the union. That gives me all the orange stuff outside of here. Right, and then I also need the intersection in there, so I need this part here. So it seems that it makes sense to set x equals to 1 and y equals to 1 and z equals to 0. That'll give me the right top, and now I need to make sure the bottom is filled in. And so that's the symmetric difference. Well, the symmetric difference is everything else. So I'll set z prime equals to 1, and there. Okay, so now the Hamming similarity fits into this framework. Okay, so let me put up a few more of these, and you can kind of have as an exercise to figure out how to go through these. Unless you have questions, I can go through more. But so the Annberg similarity is defined. This is going to be equal to A intersection B, A union B plus A times the symmetric difference of B. The size of A times, or A this the symmetric difference of B. Yeah, so this is another one that gets used, and if you know, the reason I mention these is if you're reading some like if you ever pick up a paper in data mining and you start reading it, people randomly use these different similarities, right? So I'll just list some of the most common ones. The Rogers what is this? Tanimoto similarity, we'll call this RT, A and B is going to be equal to A intersection B plus A union B complement over A intersection B. Actually, I'm going to write this in a different form that's more clear. Sorry for those taking notes. It's all in the PDF online. So it's the size of a full set minus A times the symmetric difference of B the size of the full set minus plus A times the symmetric difference of B. Right, so so this one, so the bottom is always larger than the top, right? And so the larger the symmetric difference is, the less similar they're going to be. Right? So this kind of intuitively, so this kind of makes sense, right? If there are more things that's in A and not B, and more things in B that's not A, the less similar they're going to be. This one doesn't care so much about the size of the intersection. It just cares about the things that you've misclassified, right? That you've put that are different between the two things. It doesn't care that things are the same, only cares about the parts that are different. Right? So you could, so this sort of thing comes up in you can see coming up in machine learning, for instance, where you're looking at the number of things classified incorrectly. Yeah.
So just to make sure I'm understanding this right, that one on the top, the awkward one, could you rewrite the denominator as like 2 times the size of A union B minus the intersection of A and B?
2 times the size of A union B minus the intersection. Yeah, so that's going to work as well. Yeah, you're right. So there are different ways you can write these. Yeah, so if you want to fit it into that general framework, you may need to figure out how to rewrite it so it's like that. And the coefficients don't need to be 0 or 1. And in this case, I think the right coefficient is, for the Anberg, is 1002, for instance. But there are different ways of writing these. And these set operations, there's equivalences between them, and there's, you'll see them written in various different forms. I've just tried to put them in this somewhat normalized form, or some form that's easy to interpret what's going on. And then the final one is the dice similarity. This one I see a lot when people are working in people use this a lot in imaging. I've seen. So this is defined as 2A intersection B 2A union B plus A times this the symmetric difference of B, or you can write it as 2 times the intersection A intersection B over the size of A plus this size of B. Right, so if A and B are equal to each other, then the intersection is exactly twice the size of the individual sets. But if they have some parts that are different, then the intersection will be smaller, but it'll be counted on the bottom. Right? Yeah?
Is that true that every similarity should be written down in the form of x, y, z, z prime?
Well, not every similarity, but so okay, I was about to mention there's one nice property, and I gave a reference to a paper in the notes that if it's written down in these in this form, so anything that fits this x, y, z prime model has two consequences. One is that d a b equals 1 minus s a b. This is going to satisfy this property that's a metric that we'll talk about in another lecture. So the associated distance is nice. So that means the Jaccard similarity is going to be a metric, and that there's going to be an LSH scheme that you can use with these similarities. LSH is something that we'll talk about in a few lectures as well. It's locality sensitive hashing. So we talked about hashing last week. where you hash things, these random hashing where things go to different bins. With the locality sense of hashing, what you want is you have these very strange objects, but when you hash them, similar things are more likely to collide. Okay, and all you need is some nice notion of similarity. And you want similar things to collide. Not always, but you want them to collide proportional, essentially proportional to their more likely to collide if they're more similar. Okay, and so that essentially the expected value of the collision will be equal to the similarity. So that's why you want it to be between 0 and 1. And so similarities that fit this property will have these that can be written as x, y, z, z prime will have these properties. Okay. Now, not all similarities will have these properties, but the ones that do can be written this way. They will have these properties, which we'll talk about the powers of in a few other lectures.
So it sounds like you're kind of getting at this, so that there's like a direct correlation between like the value of the similarity and if you were to the hash. There.
Well, so let's talk about this in a lecture later, because we'll kind of get into these properties later. It'll take too much to go in detail here, but hopefully we'll come back to this. The point I wanted to make, though, is that there are all these different choices of similarity, and all of these are fairly good. All of these are pretty reasonable choices. They both satisfy these properties, right? So why? I said this Jaccard similarity is a good one, right? Why is the Jaccard similarity the right one to use? Well, we'll see. It's going to work really well with the technique that's going to that's been called min hashing, which I think is the next lecture. So that it works. Yeah, min hashing is the next lecture. So we'll see. It works really well with this technique called min hashing, but some of these other ones you can use with min hashing as well, with some way of adapting it. That's basically what this second scheme is saying. The min hashing is a one that's especially nice though. Okay, but there isn't a good answer otherwise of why we're using Jaccard similarity instead of the dice similarity. There isn't, right? You have to make that choice, and you should think about what these mean when you're going to choose to use one. Draw these pictures, like this picture for the Jaccard similarity up there. Draw the picture and think: does this make sense for me? There can be variants of this. Does this one make sense, or does the Hamming one make more sense? So I'm not sure. You're going to have to make this decision yourself. Jaccard is commonly used with text, as I'll show you how next. Okay, but it may not be the only option. Okay, so this is hopefully maybe one of your first exposures, and there'll be more in this class, to the black art side of data mining. There's lots of this black art where you're making some decision that's turns out to be fairly arbitrary. Now, the guidance I'll give you in this class is which ones are going to be more computationally efficient and which ones can we say things more formally about. And you'll tend to use those, but know that that's still a modeling choice you have to make. Okay, so let's say we're going to use the Jaccard similarity. It does have these nice properties that I wanted, and some others we'll talk about on Monday next week. But how do we, this is a nice similarity or distance between sets. How do we go from these documents, how do we go from these document into a set so that what the Jaccard similarity is capturing tells us something that's about the documents. Okay, so what we'll be using is we'll consider basically two types of ways of doing this. One is called the bag of words model, and there are two kind of ways of taking a document into an abstract type. One is the bag of words, the other one is the other technique is called the K-grams. And we'll talk today about the K-grams. The bag of words, I think we'll talk about Wednesday next week as an alternative. They're both popular, and there are variants, many little variants on both of these. So what the bag of words is doing is it's turning into a vector, so that this one goes to a vector, this, like say V1, V2, up to VD, and VD is going to be very large. This is the number of all possible words, and so each VI is the number of word 2 in this case for V2 in the document. So I just take every word and I count how many times it occurs. Most of these are going to be zeros, because most words do not occur in any given document, and something like the word the is going to occur a lot of times, right? So if V2 is the word the, I count how many times I use the word the, right? And it's something like 7% of all words in some text, right? So I just count those, and that's my representation. So we'll come back to that. The K-grams is instead going to convert it into a set. It's not going to care about counts. And so what we're going to do instead is and K is going to be something like the number of consecutive words. So the bag of words lost all notion of the locality of words. If two words occur next to each other, I've lost that. So K-gram, so if my sentence, if my document is have a nice day, then a 2-gram would be a bunch of objects. Have a nice, and nice day. So I'm going to have 3 objects here. Have a is one object. A nice is another object, and nice day is another object. And so this is going to be a set. This is a set that represents that this sentence. Okay, so and this is for k equals to 2. And this is, so I've broken into these words, and now I've captured something about which words are next to each other. I haven't just looked at each words are in there, but I know that have a is next to have is next to a, right? Have is next to a is next to nice. I've kind of captured something about that. Okay, so let me show you a little bit bigger example. It's a little slow to write these things up, so let's hope this works. All right. All right. So, and I'll post these. These are posted on the website already. So here's an example. This should look similar to a book, but for copyright reasons, I didn't copy it exactly. And you'll start to see why I use this, right? So this is so this could be our text, and one way to think about it is this is just one string of text, and so if I do a K-gram with words, where K is equal to 1, then each word is an object in the set, right? But the word Sam occurs twice, but I only put it in there once, right? The word I occurs 5 times, I only put it in there once. I have not kept track of that. With K equals 2, I get a larger set here now, right? So I am Sam, Sam, Sam. And if the same word occurs twice in a row, but I still do that. So if you look at the end of the second sentence and start the first one as an am I. No, I am. Yeah, so this is going across lines 2 and 3, but I am occurred twice, right? I only put it in there once. Yeah.
Do these grams, would you ever want to do like a special character that means like beginning of sentence, and then have a gram that's like beginning of sentence?
Yeah, there, and that's a good important point. I'll come back to that. There are lots of things you might want to do, and I'll give you some guidance on some things like that, like beginning of sentence. Like often though, a period works well for end of sentence. I think beginning of sentence is less important than end of sentence somehow. Okay, so you can also do this with characters instead of words. And it's actually more often people use the character k-grams instead. So here, just showing the smaller example, and I've knocked everything down to lowercase. I've gotten rid of punctuation. I've gotten rid of spaces. Okay, those are choices, by the way. So IAM is the first three, and then AMS is AMS and SAM. And you can see that these are the character grams, and these are for k equals 4 for this whole thing. Okay, so so often people use characters. It does capture something across words still because you get the characters spanning across the word, and you probably want to use a slightly larger value of k when you're using when you're doing the characters instead of the words. Okay. So let's look at this example where I'm doing the whole document with words and k equals 2. All right. And so actually, instead of doing this, let's think of them as 4 different documents, right? D1 through D4. Okay, so I've done this, and I've turned all of these documents into just their sets. Okay, this makes sense? Right, so the first one was I am Sam, I turned it into I am and am Sam, and so forth. And you'll notice that the first and the second document, they share the element I am. Okay, so that's why I picked this kind of repetitive text. Okay, so now, what is the Jaccard similarity between various of these documents I have here? Right, so what's the Jaccard similarity between sets D1 and D2? Yeah, I mean 1/3, right? The I am is the same, and the am Sam and the Sam I are in the union, but not in the intersection. Make sense? Okay, so what's between D1 and D3? You saw that one already. They have nothing in common, right? There's nothing in common between D1 and D3. Between D1 and D4, okay. So what is? I showed it. I'll put it up again. Okay. Well, let's. So it's 1/8. So D4 is now much bigger than D2. Right, so they both, D1 and D2 have one set object in common. D1 and D4 have one object in common. But I would argue D4 and D1 are much more different than D1 and D2, right? That makes sense? Because D4 is much larger. So they're going to be less similar. So the similarity is much smaller. Right, so this is captured well by the Jaccard similarity. So that's good. Okay, so one more. Let's do D2 or let's do D3 and D4. What's the similarity between those? Huh? 3 by 11. So there should be 3 things in common. There's I do not, and not like in common. And so that's 3 things, like green eggs, eggs and ham. And so that's 4, 5, 6, 7, and then 8, 9, 10, 11. Right, so yeah, 3 over 11. And documents 2 and 4 are also somewhat similar because they both end with SAM-IM, but document 4 has a bunch of other stuff, right? So document 2 is completely within inside the set for document 4. And under this similarity measure, they're fairly dissimilar from each other. That you could think of another way of measuring similarity where you'd say the similarity is 1 because everything in document 2 is inside of document 4. Or maybe you'd say document 2 is similar to document 4, but document 4 is not similar to document 2. This would be something that's not symmetric. Okay? And so you would have to, all the ones I put up, if you notice, they're all a function of these intersection, union, and symmetric difference. Those are all symmetric operations. So all those are the same if you from A to B and B to A. But you could think of another similarity that's not symmetric, and maybe that makes sense. You'd want to say that D2 is similar to D4, but D4 is not similar to D2. That's reasonable to do, depending on your application. So if you want to do a partial match, you want to say, I want to find the string of text in a large document. I'd say if I can find it, then that document is similar somehow. So that'd be a non-symmetric operation you want to do. But in this case, we're just looking at the Jaccard similarity is symmetric. Okay. Okay, so you can kind of, hopefully that application or that example kind of made things a little bit more clear. You know, it should be pretty straightforward. So for the second homework, you're going to have to implement doing these K-grams on some documents. Okay, so just a warning. We'll probably post the documents, next homework sometime next week. Okay, so 20 minutes left in class. So what do I want to talk about? Okay, so what? So you know, as I've mentioned, there were a lot of things I did that I didn't really explain. I didn't really explain why. There are a lot of modeling choices I made in how I created those grams, those sets, right? And so it seemed to work fairly well. The sentences that seemed similar had a higher similarity. None of them really approached 1 unless I did the similarity with itself. But they were. I could distinguish between the more similar and the less similar sentences, right? But what were some of the choices I made? Let's just discuss these, and maybe I can tell you what as I know is more common or less common. All right. So what are some people point out already? I mean, the first one is words versus characters. Okay. The first time I learned about these K-grams, I thought, okay, clearly it makes more sense to do this with words. You're really capturing more of the meaning. If you're using characters, you're kind of splitting up the meaning. Turns out, in many applications, using characters is much more common, especially for very short text. So, you know, when this was first, a lot of the technology for this was built for web pages in the early days of the web. So the next few lectures are technology basically really fleshed out, developed, in some cases developed by the very first companies to build these search engines on the web. and so there, I think these web pages back then, as they are now, were kind of fairly long. There'd be hundreds of if not thousands of words on a web page. So if you're doing something like that, you may want to do words. But now, most of the text this is being used to analyze is something like on Twitter, right? A tweet may have only like, 8 words in it or something like that. And so you're going to get very small similarity between things if you use words, where if you have misspellings, maybe the characters are going to pick up on stuff that is common despite the misspellings, right? But maybe you want to highlight if things are spelled differently, it means something different. Like if you said bruh instead of bro, right? Maybe that means something different. I don't know. I never really quite understood those distinctions, but I was not cool at the right time, I guess. I think I'm cool again because I don't say bruh, but I'm not sure. Okay. So this is kind of a big distinction. There's also the choice of K. Kind of the choice of K, again, you will kind of want to do this with the larger the amount of text, the larger K you want to do. You're kind of can capture things spread further apart with larger K. But you need more text before you find similarities. If your K is too large, too many of the similarities are going to be too close to 0 for it to be useful. As K is smaller, you're going to get higher values of similarity. Because essentially at K equals 1, say with characters, you're just getting the count of the number of times each letter is used, and that may not share any meaning, but it gives high similarities, right? So there's some trade-off here. So I think in general, let's see, so this isn't the area I work in, but from talking to experts, for words, K equals often either 2 or 3 are pretty common, and for the character, so often K equals 3 or 4, kind of in that range. You can play with it and change a little bit. And again, the smaller the text, the smaller the K typically you want to use. So what are other choices I made in those examples? Okay. So capitalization, right? So if I was doing K-grams with characters, right, I had Sam in there. Is this equal to a lowercase a? This was meant to be uppercase a. Right, are these equal if I have an uppercase A and a lowercase a? If you're talking about the sound of it, maybe it doesn't matter if you're talking, but if you know that S is for a proper name, you want to highlight that, then make them different. But the more different things you do, you're going to kind of have a lower similarity again. It's like having a larger value of K if you allow capitalization. Right? It's more flexibility, but it's a larger space you have to search over, so you're going to have your similarity values are going to be lower, and you're going to be harder to distinguish things if everything is very low. Right? So you're going to have this trade-off. Also, in different cultures, even if they're both speaking English, they may have different kind of patterns of when something is capitalized. So this is even more true if you're talking about punctuation. Right, so if I kept a period, especially if I'm doing charactergrams, if I'm doing wordgrams, so I want to leave a period at the end of a word to say it's the end of a sentence. Or do I want to even have a special character that says this is the end of the sentence or the start of the sentence as one of the words? sometimes people do this. This can be useful to distinguish the end of a sentence. And a period does not always do that, right? So I could say PhD period. This does not necessarily mean the end of a sentence. This is just the way, you know, this is typically written in text. Or if you write Mr., you know, it has a period. It doesn't mean it's the end of a sentence. So whether you use punctuation or not, also across cultures, there may be different choices of punctuation. Maybe you don't. If someone took a document and just changed how they did the punctuation, you still want to say it should be fairly similar. So often people will remove the punctuation out of the sentence. So it's fairly common to remove the punctuation because it kind of just sometimes just gets in the way and doesn't help that much. Should there be a comma someplace? You know, some people will put a comma, some people won't. The Oxford comma, for instance. Let's see. So one other common thing that's used or is paid attention to is if you're doing these shingles or these K-grams with words, is you want to look at these stop words. So these are very common words that don't necessarily mean add a lot of specific meaning or kind of aren't like telling one sentence apart from the topic of a sentence much. So like and that it is like if you use these words, they're not really adding so much. If you're trying to figure out the topic of something, that's not helping you because these are just going to appear everywhere. So one option is to just remove these words. So it is to skip all the stop words. So just skip over them, pretend like they're not there in the document. So that's especially so there are these things called there are these techniques called that are called topic models that I'll mention. They're kind of taking this and then building some other techniques we'll talk about later in the class. I'll come back to them. They're trying to kind of find these groups of documents that are all on the same topic, like politics or sports. And these words are not really helpful in distinguishing, is it about politics or sports? All of them use the word a or the or something like that. So that doesn't really distinguish. But there's something else that can be useful for. Often, if you see the word the, and you're doing a K-gram with size 3, the K-grams that start with the word the and of size 2 or 3, these are often very meaningful ones because they've picked out some important piece of text. The tends to, or tends to highlight some subject of the sentence, and I'm not an NLP expert, but so if some will only look at K-grams of size 3 that start with the stop word. Right? These will sometimes be much more informative than other ones. So sometimes you want to use the stop words to highlight certain aspects. And so there's a lot more things you can do getting into this in these nuanced parts. Sometimes look at parts of text that help you pick out key elements of a sentence that have more meaning to it. Right? All right, so again, there are lots of choices here in how you do these K-grams in order to build these sets. Okay, so let's kind of just review this pipeline. So I have, this this document, and so I turn it into a string of text. Then I use K-grams to turn this into a single set. And then I would use, say, Jaccard distance or Jaccard similarity to measure the similarity or distance between this document and another document. Right? So I did this with another document here. So also into a string, into a set with k-grams, and I would use the same k-grams, and then I could go to this Jaccard distance or similarity and then say how similar these are. Right? So this is kind of something we'll see over and over again in class, where you take something that's messy data, and what you're doing is you're converting it into kind of nicer and nicer objects until you have this well-formed distance or similarity measure or algorithm that you can use to say something about it. If you just started with these documents, there's lots of stuff you might want to do. Like if you're dealing with web pages, it was much more common, and I think this is still built into search engines. They don't just look at the text, they look at the metadata of it, right? So there's like a title tag, and there's all other things you can tag. The hyperlinks will turn out to be really important. There's lots of other data you can do, but in this case, we've simplified it down to just a string. Okay? Once we had it as just a string, we had some choice of k-grams. And how we did this, there was some choice. And then we chose the Jaccard distance as the way to measure the similarity between these sets. Okay? And there are choices everywhere in this pipeline. And this will come up over and over again, that we're making these modeling choices in order just so we can say the similarity or distance in this case. Right? There are going to be other choices in the algorithm. One is more efficient than the other, but that one has much better accuracy, or there are going to be various trade-offs, and this is going to happen over and over again. So in this choice, in this case, we just assumed we didn't even discuss until this very end that why would you not just do it as a string of text, right? But that was a choice, and then if you change how you do the k-gram, it's going to change how well it works. And a lot of these are valid choices, and there's not necessarily a right answer. People do a lot of trial and error of trying different things and see how they make sense, and you're going to have to do that. When we were talking about the similarities, people were asking about the border cases, these similarities. What happens with this is the empty set? What happens if this is 0? Those are great ways of exploring, does this make sense? If you're trying something, take a document and say process it with k-grams. Look at the k-grams and see if those seem like they might be useful. If you take two documents, see which k-grams overlap and say, oh yeah, those have picked out the really important part of why those documents are similar. Okay, and so we'll do this with some of the homework. Okay, I'll give you, well actually you'll get something, probably I need to finalize it, but we'll get something at the point of the string. You'll get strings of text. You'll have to make choices on the k-grams, and then you'll see how well they work at Jaccard distance. And then we'll apply some algorithms to do some more efficient stuff afterwards. We'll talk about in the next few lectures, and you'll try vary with those as well. So cool. So just give you a preview in the next lecture. Now that we have a way of measuring similarity between documents, the problem is going to be that we're going to have a lot of these documents, and we don't want to just compute this similarity between all of them, right? So if you have n documents, and n is large now, all the pages on the web, or all of the tweets that you have, or all of the emails that I get, I don't want to check it against every other document, or I don't want to check all pairs. How do I more efficiently find the ones which are similar to each other without having to check all of these calculations? And so it turns out that some of the structure I mentioned about the Jaccard distance is going to be useful in doing this more efficiently. So next lecture on Monday, we'll talk about how to do that. All right.